Hello. Also, Daniel, don't forget to rename yourself before we start.
Yep, you're good.
Okay, awesome. Hi, guys. It's very nice to meet all of you. For those of you who don't know, if you want your messages to be read by us, send it as a direct message to Chat Relay, and it will appear here on screen. And we have a lovely team of moderators working with us, and so they'll be making sure that chat stays positive, but also, if you send a good message, then you'll get a star, and the stars can accumulate, which is really nice. So I believe we have someone from Math Kangaroo here to say a few words.
Yep, hello everybody. I'm Alan. I've been doing the Math Kangaroo competition since first grade actually, and have been doing it nearly every year since. I think it's a great introduction to math competitions. Really helped me start thinking of math as a puzzle, as math problems as puzzles to solve, rather than say arithmetic to grind out. I think these problems are going to be really fun, personally. I think I should introduce our co-hosts then. We've got Megan Davy. She enjoys participating in math competitions locally and nationally. She represented Nevada at Math Counts Nationals. She's qualified for Math Prize for Girls. She's president of her school's math club, and as well as active in her local math club. She's on the competition team, volunteering over 100 hours per year, and she also plays violin and speaks Spanish. That's Megan. And we have Daniel. He loves solving math problems, competitions, or modeling. He loves teaching. He's currently the head coach of a Math Counts team, and he also enjoys playing the cello. So give it up for them.
Most definitely. I'm very excited to be joined here by Daniel today. Actually, Daniel, have you popped on camera yet today?
I have not, I think. Hello, everyone. I'm Daniel.
Yes. So we're very excited to be here today. And of course, our goal here today is just to solve some problems. Live, of course. We have not seen these problems yet, but I think we should probably get started with this first one. I should be able to see it on my screen, and it says, some shapes are drawn on a piece of paper. The teacher folded the left-hand side of the paper over the thick line. How many of the shapes on the left-hand side will fit exactly on top of a shape on the right-hand side? So as you guys can see, we have 5 shapes on each side, and we're just going to try to see which of them line up. And so the first thing that I notice is that we have 2 triangles, 2 arrows, and a circle, and triangles have direction, position. Those 2 positions don't line up because the circle over here is right next to the edge. And the circle over here is not. If we look at the 2 arrows though, so this arrow position-wise maps to this arrow, and they're both pointing inward. So those 2 line up. And this one maps position-wise to here, so those also both line up. Because those are both pointing down. Now if we look at the 2 triangles, this one has a corner in the bottom outside and position-wise maps onto the same square as this one, which also has a one in the bottom outside. So the first triangle is a yes. But our second triangle over here, they map position-wise, but this one has a corner on the bottom outside, away from the line, and this one's corner is closer to the line. So the other one is wrong. So if we count how many work, I think we have 3 that work, which is C, like you guys are saying. So yeah, good job.
All right, let's move on to the second problem then. And this one is a word problem. We have...
Daniel, you'll notice a lot of these are word problems.
Very true, actually. So we have a person, and not a person, sorry, a number. A number is less than half. Sorry, it's more than its half, and it's... No, sorry. It's less than its half and more than its double. There we go. And also, the sum of me and my square is 0. So let's call this me x. So what do we know? We know that x is less than half of x. Also, x is greater than 2x. Well, if x is greater than 2x, this would mean that 0 is greater than x, right? Because if we subtract x from both sides, we get 0 is greater than x. So first of all, we can eliminate all of these answer choices. And our second condition is that the sum of me and my square is 0, so x plus x squared is 0. Well, which one of the answer choices satisfies that x plus x squared is 0? Negative 2 plus negative 2 squared would be negative 2 plus 4, which is 2. So that can't be it. So our answer has to be B, negative 1. And if we check, negative 1 squared is 1, and negative 1 plus 1 is 0. So negative 1, B, is the answer that satisfies our conditions.
Yeah, and I think we can even get this answer without the multiple choices, because if you see, the sum of me and my square is 0 is simply a quadratic equation. X plus x squared equals 0. And so we can factor this, x plus 1 equals 0, which means either x is 0 or x plus 1 is 0. And so, like Daniel mentioned earlier, we know that x is strictly less than 0. So yeah, it has to be negative 1. So yeah, great job. Okay, what's next? There are 5 candidates in the school election. After 90% of the votes have been counted, the preliminary results are as follows. How many students still have a chance of winning the election? Okay, so the first thing I want to know is how many votes haven't been counted. We know that 90% have been counted. And 10% haven't. So how many votes have been counted? Well, if we add them up, 14 plus 11 plus 10 plus 8 plus 2, that's 45. So we know this is 45. And so if we do some math, then we get that there are 5 remaining. There's a few ways to do this math. The easiest one is to divide 45 by 9, because 90% is 9 times as many as 10%. You could also divide 45 by 90% and then take 10% of that. Basically, lots of ways to do that, but we get 5 votes haven't been counted. And again, 50 votes total. So to win this, I think they just need to have the most votes, though. Yeah, because you can't win this if it's a majority or anything like that. So to have the most votes, well, clearly Alex can win if all of the votes go to Alex. So Alex is A-okay. For someone else to win, they have to beat Alex. They have to get more than 14 votes. Could they get 15 votes? No, could they get 14 votes? What happens if there's a tie? Good thing to know. You can't have a tie, because there's no number 5 less than 14. So, who can get more than 14? Well, Bella can, because 5 plus 11 is 16, which is more than 14. And so can Calvin, because 10 plus 5 is 15, which is more than 14. Diane can get at most 13, which would still have Alex win. Eddie can get at most 7 votes, which would still have Eddie in last place. So, no offense to Eddie, but he is not winning this. But how many people can win this? 3. And so let's check that. Yeah. Yeah, I do feel sad for Diane and Eddie.
All right, our next problem. Wow, another word problem. Who would have guessed? So we have Arpit. I have no clue what creature Arpit is, but we have Arpit. And he wants to move from hexagon X to hexagon Y. But he wants to pass through all of the 7 white hexagons. So we want to find the number of roots. Well, notice that if we start at X, first thing we have to do is move to not Y, sorry. We have to move to this square, right? Because there's no way to move from X to any other square. So that's the next square we have to touch. Well, from here, Arpit has options, doesn't he? He can either go here, he can go here, or he can go there. Well, what happened if Arpit went there? Arpit went there. Then no matter what path Arpit took from that square, there'd never be another way to get back to Y, because the only square that goes to Y is this square. And Arpit wants to go through all of the hexagons, so if he already travels to this square, he has to go through all of the rest of the hexagons, but he can't ever get back to Y. So he can't go there. Let's look at the next option, which is he moves into the center. What happens if he moves into the center? Well, from the center, he looks to have 5 moves. He can go here, 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 or there. But if he moves here, again, we have the same problem, right? He has to go to Y, this square is the only square that goes to Y, which means he can't go to this square without skipping all of the rest of these 4 squares. And from this square, he has to go that way, because if he tries going this way, he can never get to Y. And same for this one and this one. So the only possible route for him to take is if he goes to the center first, and then wraps around. So that's one way. So what if Arpit, instead of going to the center, goes left? So he goes to this square. Well, at this square, he has the option to go to the center, or he has the option to go here. If he goes to the center, again, we have to have him go to the leftmost square and then wrap all the way around. And if he continues on, he again is faced with the question, do I go to the center or do I wrap all the way around? And what happens is actually, at every move, or at like every other square, you can either move to the center and wrap all the way around, or move to the next square. So basically, all the paths that are possible are he moves 1 this way and then goes all the way around. He moves 2 this way and then goes all the way around. 3 this way and he goes all the way around. 4 this way and he goes all the way around. Notice he can't go all 5 squares, right? Because if he goes all 5 squares, there's no way for him to get to Y and the center square, because if he goes from this square to the center square, there's no way to get back. So they're actually going to be 1 plus, let me count that, 1, 2, 3, 4. 4 for a total of 5 ways, I believe.
Yeah, I think that's a bit of an unpopular opinion with chat, though, so I might want to go over that a little bit more. And so one way that we can think about this, right? So we know that if we go to the center, right? So suppose we've come out, we've gone around a little bit. If we go to the center and don't go back to this next point right here, then we won't ever be able to reach that point. Because say we go somewhere else, say we go here. What we've essentially done is blocked off this point from this point. So there is no way for us to hit that point again. So whenever we go to the center, we have to immediately go right back to the next one on the outside around here. So given that, we have basically a few options. We know we have to go here, and we know that we're going to have to be going around like this and then go up here. But what we do have a choice for is when we go to the center. So we can go to the center right away and then go around. We can go over 1 and then around. We can go over 2, then around 3, or 4. But another way to think about this is simply, do we want to skip here, 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 here? Which of those lines do we want to skip over in favor of hitting the center? And so since we have 5 choices for which line we can skip over, then that would make our answer 5, which is option D. Yeah. So does that make a bit more sense? If you guys have questions about this, please do let us know. Okay, awesome. Okay. Well, if there are no questions right now, I'll move on to the next one, but if that changes, let me know. But as for the next one, it says, 3 children asked their grandmother how old she was. She replied by asking them to guess her age. One child said she was 75, one said she was 78, and one said she was 81. It turns out one of the guesses was wrong by 1 year, one by 2 years, and one by 4 years. What is the grandma's age? Okay. I feel like a number line could help us here. So why don't we get one of those? So, beautiful line, no numbers on it yet. Let's change that. What numbers are we given? Well, 75, 78, and 81. And you'll notice each of these differ by 3. And then we know that we have one that's off by 1 year, by 4 years, and by 2 years. Now you'll notice 1 and 4 differ by 3. So what that means is that we are going to have something that's either like this or like this. So 1 from the middle, and then 4 from the one that's 3 away from that. And you'll notice that it has to be 1 from the middle so that the 1 and 4 are going the same direction. So 1 this way, 4 this way. So, well, what numbers are 1 from 78? Well, 77 and 79. And of course we can check this. 77 from 75 is 2, 77 from 78 is 1, 77 from 81 is 4. 79 from 75 is 4, 79 from 78 is 1, 79 from 81 is 2. So, what is our answer? Well, it looks like B or C could work, but read our answer choices carefully. 76, 77, 79, 80, it cannot be determined exactly. We can't figure out what it is. So the answer is thus E.
Yeah, this problem is really tricky because if you just look at the answer choices to try to solve this problem, like I know some people did, and you see either B or C and you plug it in and it works, it is very, very tempting to just put that down as your answer. But you always want to make sure to check all the answers and go through the math in order to make sure that your answer is actually correct. Because in this case, B and C both work, so the answer actually has to be E. All right. Our next problem involves geometry. Ew, just kidding. So we want to find...
No need to apologize for being wrong. Or for being right. Sorry, you're right. Geometry, you.
factual opinions. So we want to find the length of SV, given that W is the midpoint of a square, C is the midpoint, U is the midpoint of SR, and that these three have equal area. How could we do this? Well, one thing we can note is that if these three have equal area, then they all have area 1/3. And let's just focus on this one for now. So yellow has area of 1/3. Since W is the midpoint of it's the center of the entire square, we know that WU has to be 1/2. And since U is the center of SR, SU has to be 1/2. And here we have a trapezoid whose height is SU, which we can determine, and which one of the bases is WU, which we have already found to be 1/2. So the area of a trapezoid is going to be the average of its bases times its height. And we also know the area is 1/3, which means SV plus WU divided by 2 times SU is equal to 1/3, which means, well, we know SV is equal to, let me do the math real quick. So SU is 1/2, so divided by 2 again, that's 1/4, multiply it on the other side, and you get SV plus WU is equal to 4/3. We know that WV is 1/2. Sorry, WU. I cannot write for the life of me. But WU is 1/2, so we get SV is going to be 4/3 minus 1/2, which is going to be 8/6 minus 3/6, which is 5/6, which is answer choice E, I believe. Megan, I think you're muted.
I would be. I was just going to say that I think that there's another way that we could approach this that allows us to do one of my favorite things to do in geometry, which is where you just draw a line and then it makes your work a lot easier for no good reason. So, if we're looking at our diagram, right? What happens if we split our square into quarters? So, you'll recall that this is supposed to have, each of these is supposed to have 1/3 of the area. Oh wait, actually I'm going to draw a couple more lines. Let me draw this line and this line. So you'll notice that this area, and this area are all 1/4 of the area of the square. Now, so to make up for that extra difference, our pentagon has this area and this area, whereas each of our trapezoids just have this area. One of them has one of each, effectively. So that means whatever this is that doubled. We know these sum to 1/2, so 1/6, 2/6. What's 2/6 plus 1/2? 5/6. And that is how you solve this, by drawing lines that you might not have known you needed to solve, because that is the true essence of geometry. But yes. Okay. Oh, no. Oh well. Okay. Two congruent isosceles right triangles each have a square inscribed as shown. The square marked P has an area of 45. What is the area of the square marked R? Okay. So we can definitely just bash this out. So the side length of P, square root of 45, which makes the side length of the triangle well, double that, 2 root 45. You'll notice within R that if we take this part, that is the side length times the square root of 2, and this part is the side length over the square root of 2. And of course, that also sums to 2 root 15. And so then we get to do some very fun mathematics where we say S is equal to, 2 root 15 over root 2 plus 1 over root 2, which is absolutely atrocious. Oh, someone is very smart and said side length R is 1/3 of the hypotenuse. Yeah, that is objectively actually a superior way to do that. So the hypotenuse is root 2 times the side length. So root 2 times 2 root 45 all over 3. And you'll notice that that's true because the side length of the square is the same as that bit and that bit from isosceles triangles. So yeah, if you do the math, I believe that cancels out to 2 root 10. And then of course you square that to get 40. Yeah. And I believe that this would also pan out similarly. For those of you who don't know what you do with this abomination of a mess, basically the first thing we do is we get rid of the nested fraction. So that is 2 root 30 over 2 plus 1. And that
The entire side length would be 6 root 15, right? Oh, sorry. Wait, how'd you get 2 root 15? Sorry.
From up here, that was the side length of the leg length of our triangle.
That would be 2 root 45, right?
Yeah, okay. Most definitely, yeah, no, okay. That would explain a lot. Okay, yeah, 45 times 2, that's 90. Okay. Keep your numbers correct, kids. Otherwise, you make very silly mistakes. For example, 45 times 2 is not 45. Okay, and then from there you also get 2 root 10, which still squares to 40. So yeah, that is B. And the reason why it's not 45 with that factor of 3 is because so we have the square of the area marked R. So what we're actually looking at, 45 has a factor of 9 in it. Take a square root of that, that's a factor of 3. And we're ending up dividing by 3 because of how the math worked out.
All right, awesome. Don't forget to keep your work nice and tidy so you don't make copy errors, because those are the worst kind of errors. All right, next problem. Oh, this looks pretty cool. We have a cube. That's a lot of text, by the way. But we have a cube, and each side has either a circle, a square, or an X on them. And we want to find which one of these could possibly be the sides of a cube. Well, one thing we could notice straight away is if you look at any corner of the cube, for example, like, I guess the only corner visible to us is going to be like the one on the top right. But if we look at that corner, we can see 3 distinct objects. Does that always hold?
I think so. Yeah.
Yeah, because if we have 3 corners, they're all right next to each other. And any 2 squares that share a common side have to have different shapes on them. Which means if I had an x here, this top one could be a circle or a square, but no matter what that one was, the other side has to be the other one of them. So if that top one is a circle, this one has to be a square. And if this is true for every single corner, that means every single corner will have 1 x, 1 circle, 1 square, and there are 8 corners, which means there should be 8 circles, 8 squares, and 8 x's.
Yeah.
But none of these answer choices have 8 circles and 8 squares, right? Which means the answer has to be E, none of the above.
Yeah, an important thing to keep in mind here also is not only are there 8 corners, but there are no things that aren't corners. So if we had like extra stuff, like a 3 by 3 by 3, then it wouldn't all be corners. So it might work out to be one of these. It still wouldn't, because none of them are at least 8, but yeah. So yeah, very keen eye. Yeah, good job, y'all. Okay. The lengths of the diagonal of squares ABCD and EFGB, okay, are 7 and 10 centimeters respectively. Point P is the intersection of the diagonals of square ABCD. Okay, what is the area of the triangle FPD? That is, anyone want to do a coordinate bash? Looks like Daniel wants to do a coordinate bash, so that's the plan. So for those of you who don't know how we do a coordinate bash, basically what we're going to do is we are going to pretend that this is on the Cartesian plane. So the important points for us are that F is going to be 0, 0. Coord bash is conceptually simple for this problem, but not likely computationally. See, okay, the thing is, we're just chord bashing a triangle. And if you have a triangle with one of the places with one of its points at 0, 0, it's not that bad. So basically, yes, for those of you who are confused, we are plopping this on the Cartesian plane. We are giving each of these points a coordinate. So for example, you'll see that the diagonals are 7 and 10, so that means the side lengths are 7 over root 2 and 10 over root 2. So we can use that to find fun stuff, such as that. Okay, so what points are relevant to us? D. Where is D? Well, D has a x value of 10 over root 2 minus 7 over root 2, and a y value of 10 over root 2 plus 7 over root 2. I don't want to write that though. 10 minus 7, that is 3. 10 plus 7, 17. And what is the other one that we care about? Well, the other point that we care about is P. And so P is over from D, down by 7 over 2 root 2, and over by 7 over 2 root 2. So that makes P, goodness. Okay, 6 plus 7, 6 because I double it, so 13 over 2 root 2, comma, okay, 17 doubled, 34, minus 7 is 27. 27 over 2 root 2. So those are our coordinates. Oh, someone said Pythagorean. You know, you're not wrong, but there's nothing wrong with a coordinate bash, okay? So, now that we've gotten this, time for our good old friend shoelace theorem. So, 0, 0, 3 over root 2, 17 over root 2, 13 over 2 root 2, 27 over 2 root 2, 0, 0. Heron, no. Okay, that's 0. 13 times 17, well, that is 221 over 4, and that's 0. That's 0. 3 times 27, that's 81 over 4, and that's 0. What's the difference between 221 and 81? Well, that is 140 over 4, which is, okay, right, okay, so 140 over 4, which is 35. So now that we found the difference, we take half the difference, which is 17.5, and that is our answer. But someone said Pythagorean theorem, which seems a little bit smarter, and I think Daniel was laughing at me. Okay, so if you wanted to use Pythagorean theorem, then are you supposed to find PF or FD directly? Do you know, Daniel?
I would say I think the easiest way we could solve this is if we like drew a rectangle around this and like took out those areas.
Yeah, that would also work. It wouldn't be my favorite because you do have to either draw something down through, basically you have a lot of square roots.
Yeah.
So it's not that much more nice than the other things, but most definitely functions.
Yeah, I feel like
okay.
Heron wouldn't be great for this realm because like
Heron
fractions and
seems
herons.
atrocious.
Yeah.
Okay. Oh right, yeah, no, you can't even Pythagorean theorem because okay, why? I saw that, I was like, oh my goodness, they're so smart because like DPF looks like a right angle, and it's just not.
Yeah.
I did not look at that long enough. Heron seems like the death of this. Okay, but I think the Math Kangaroo person, being a Math Kangaroo person, knows a thing about Math Kangaroo.
Yeah. There's a little trick here.
Of course
Check
there
out
is.
check out triangle FBD. That is a right angle because 45, 45.
FBD.
Oh.
So you
Wait,
use
it is?
times height over 2 there. Height is length FB 10.
No, FBD can't be a 45, 45, 90 triangle.
Sorry, it's just a right triangle, I mean.
Oh, yes, okay, it's
Yeah.
definitely a right triangle.
The height is 10. The
Oh.
base is half the second one, 7 over 2. 7 over 2 times 10, all over 2, 17.5.
Alan. Hi, for those of you who don't know, this is Alan Kapler. He was Math Counts Countdown Nationals, and many other impressive things that I am not fully aware of. He is annoyingly smart, and in this instance, very correct.
Yeah.
I still like Quick Match better though.
Yeah, for those of you who don't know what he said, Daniel has a picture Basically, you find the area of FDB using DB and FB as perpendicular to each other, and you take half of that because they share the same height but half the base.
That is so smart. Oh man. Alright. Let's move on to the next problem. And I think this is the last problem actually. Interesting.
Looks like it, yeah.
I would say this one doesn't look as hard as the last one actually. But we have a bunch of holes actually in a cube where every face has a hemisphere just taken out of it. And we want to find the diameter of each hole, knowing that all of them are tangent to their neighbors. Well, if I just like take a point on the top, the middle of the top here, and I take the middle of the side here. If I like draw this line here and I draw this line here, well, half the side length is going to be 1, because the cube has side length 2, right? Which means the line connecting both of them has length √2. And what else do we know? Well, we know these two hemispheres touch. And if they touch and are tangent, it's probably going to be this distance, which means 2 radius touching each other will have length √2. And how convenient for us that 2 radius is equal to 1 diameter, which means diameter will just be c √2.
Yes. Okay, so I'd like to add on to that real quick. Daniel said they are probably going to touch. They actually will touch. And the way that we can figure this out is if we take a cross section down the middle. So we can either take it in the XY direction, so like this, or like this. Whichever way, if we chop it in half, then we'll get something that looks kind of like this. And you'll notice they're all touching, and if you draw from the centers of the 2 adjacent ones, then you will get that little segment, which was √2 again. So yeah, not to scale. Nothing is ever to scale. If you look at a diagram provided in a math competition, it is not to scale. I went to a math competition where they were talking about having circles. Do you want to know what their diagram showed? This was their diagram, basically. They had a circular target. This was their diagram. They had full access to make circles. They did not. That does not mean that I should assume they are ovals. They were circles. It was certainly a competition. Okay, so like Daniel said, that is the last one. That answer is C. Here is a thing that says, thank you for joining us. I would like to say that there are 15 more minutes and no more questions. So we would love to answer any questions that you guys have about anything that we've gone over, anything that we haven't gone over, why Alan is so smart. If you can answer that one, I would love to hear it. Why Daniel is so smart, that's also one that I've got. Or if you guys just want to chat a little bit, or you can also just go. Basically, we don't have any more questions, but we do have more time. How are they so smart? Good Lord, what is that word? Okay, 2 reasonably solid objects. Okay, given a solid ball in 3-dimensional space, there exists a decomposition of the ball into a finite number of disjoint subsets, which can be put back together in a different way to yield 2 identical copies of the original ball. So you do it by scattering an infinite number of points. Okay, what did someone want from that? Do you like lemons? Maybe. Would you be okay if answering a question from the AMC 10? So, in case you did not know, we actually do offer AMC live solves. Those, if you go look at... Shoot. Debbie, can you drop the link for where to find the AMC live solves for them? But anyhow, if you want to go find that, I believe we'll be solving this year's stuff relatively soon. As for that particular question, maybe. I do not know. Thank you for hosting. Thank you for attending, Dylan. This would not be nearly as fun without you guys here. Someone asked if I like lemons, as the fruits are... As far as the fruits go, they're pretty decent. Read about the epsilon delta definition of a limit. I know exactly what the epsilon delta definition of a limit is. It completely destroys the necessity for infinitesimals. I think you have not read the epsilon delta definition of a limit, because last time I checked, it definitely requires stuff getting infinitely small.
Wait, does it? Isn't the epsilon delta definition like it has to be epsilon? No, it has to be delta away for like given epsilon.
Yeah, it's for all epsilon greater than 0, which includes epsilon infinitesimally small. So I'm not sure what they're trying to get at.
Well,
I'm also not sure why they assume I have not seen the epsilon delta definition of a limit. Like, I saw that in 9th grade, but...
there is technically a difference between arbitrarily small and infinitely small.
What is the difference, Alan?
So you can when a number it can be arbitrarily small, it can get as close to 0 as you like, but always staying within the real numbers. Infinitesimals are an entirely different plane of numbers. Look up Levi-Civita. I'll put that in the chat. They're a fun thing, shall we say?
Fun.
Yeah.
Okay, well, do you know what Matthew is talking about? Like, is he making a valid point? Because I am a little bit confused and not enough educated on the infinitesimals, but also pretty sure what he's saying does not make sense. What? Yeah, I know how you define deltas, but what does that have to do with infinitesimals? No mention of infinitely small values. That... Matthew, what are you trying to get at here? Epsilon delta rocks. Epsilon delta is the current bane of my existence in my analysis class, so I'm going to disagree with you on that. You are never changing my mind either.
Look, I'm just gonna say this. Epsilon delta exists for 1D limits and 2D limits, but it also exists for 3D limits. And let me just tell you right now, you will never, ever, ever want to use epsilon delta for 3D limit proofs, because it's so toxic. Like we did like the example of,
Yeah,
go ahead.
I was talking to, you know, geometric probability, right? You have like 1D, 2G, 3D. I was talking to a friend, she was like, oh yeah, like, you can... I was doing a problem with 4-dimensional geometric probability once, and I'm like... Basically, my friends are too smart for the good of the planet. Yeah. 3D epsilon delta. Can you do it with just epsilon and delta? Do you not need another one?
Yeah, so there are actually two definitions for epsilon delta in 3D. And one is like you have your delta as like a radius, so like a sphere. And then the other one, sorry, your epsilon as a sphere. And the other one is like you have an epsilon as a cube. And both of them like do the same thing. It's just 3D limits are so
Cube.
bad.
Like, I get why you would do it with a cube, but like visually, that is because they're not equidistant. But like computationally, it seems so much nicer. But anyhow, I'm glad we concluded that Matthew is just wrong. Like, I don't even know if what he was saying was correct, but he's just wrong. I don't even know if he's still in the Zoom call to hear us. How many people are still in the Zoom? Maybe. That is not a number. Matthew, irregardless of whether this technicality is correct, you're still wrong. Okay. Well,
Wait, what is the point you're
irregardless.
trying to make here? I'm so confused. Because we were talking about something about breaking down a sphere, and then we went to infinitesimals, and then we went to limits.
Oh, no, yeah, don't worry about it. Yeah. Well, if there's no other questions, assuming there's not many of you left in the main room, we should probably close that off and sign out for the night. But yeah, thank you guys for coming. It was a lot of fun.
Bye, everyone.
Bye. Oh, and W, let me know.